Hey, welcome to Science Sci-Fi, connecting the public to science and technology through storytelling. And today we have with us a special guest, Jeff Krehmer, who wrote this book, Infinite Resource, about how, I'm not sure exactly what to say it, maybe how to create
Let me take it
plat.
from there. So I got the book here too. How to sustainably develop the Arctic by supplying green hydrogen, fresh water, and healthy food to the world while mitigating the negative effects of anthropogenic climate change. I've said that enough now that it almost rolls off the tongue.
Yeah, I think I also try to solve issues like energy in general, which is one of the most important things in order to progress our civilization forward.
Mhm.
And you address many other stuff. One of the things I remember from the book that I like, for example, I'm very trying to propagate a colonization of space, and you can actually simulate an isolated environment in the Arctic that could be very similar to a colony on Mars or something similar in outer space. And also my day job, I work in IT. So what happened right now in IT is completely crazy, especially with AI and
Yeah.
with data center. And currently, NVIDIA is shooting through the roof. And what happened right now in IT, that a big shot, they're expanding because of AI. It's expanding like there is no tomorrow, very fast. Right now, the shortage is chip production. But within a few months, maybe 1 year, at least Elon Musk is saying that, we will have enough chips to cover all the demand, and the big problem will actually be energy
Right.
and
And I was
cooling.
just, yeah, I was just reading an article about how I think it was Ohio, one of the states is having problems meeting their energy demands because of the increase in artificial intelligence data centers drawing so much power. And it's not like they're the most of, they have the most data centers in the states or anything like that. So,
Yeah, I work in a few data centers in Calgary, where I work right now is also the data center. And I know that we also spend a lot of money on cooling. Now, if you build a data center in the Arctic, you can also have very cheap energy, and also cooling is pretty much covered up. You
yeah.
don't need to spend energy on cooling.
Yeah,
And
and Microsoft has actually done some experiments where they essentially built a data center and a pressure vessel and then put the whole thing underwater. And they just use, because of the high efficiency of the heat transfer to the water and because of the relatively cool temperature of the water, they got their cooling for free. And what they also found was that they had fewer errors than a traditionally cooled data
okay,
center. So.
so perhaps we should start with the beginning and let us know about your idea and what your platform and how we are going to generate energy.
Do you want me to like I've got some slides and stuff. We could go through the slides and
Yeah.
maybe that would be easier for people to visualize things as I'm talking.
Okay. Can you share screen? Do you see that option?
Let's see. So I think I have to be a co-host or something to be able to share screens. Oh, actually, I do see share. Yeah, host disabled, participant screen sharing is what it says now. So you'll have to edit this stuff out, and it'll take me a moment to find the presentation.
Okay, so I'll do a pause in the recording and we'll continue once we have it.
Okay,
Okay.
sounds good. All
Back
right, so
to
this is a presentation that I tried to pitch for a conference that was earlier this year, and they didn't select it as one of the ideas to pitch. But an introduction to ocean atmosphere temperature differential energy conversion, what I call OTEC. And if anyone's familiar with OTEC, ocean thermal energy conversion, this idea is very similar, except instead of using the temperature difference between two layers of the ocean, we're using the temperature difference of the ocean. And in the Arctic, you've got a nice insulating layer of ice, and then you've got really cold temperatures above that. So we're taking advantage of the temperature difference between the liquid water and the atmosphere. So this is all the energy that's consumed in the world today by human beings in various forms. So you can see we've got traditional biomass here. So that's your wood burning stoves or dung or whatever you're using to cook your food. Then you got coal, then you've got oil, natural gas. nuclear, wind, hydro, solar, and then other biofuels and other renewables.
Yeah. I personally thought that the renewable will be a bit bigger, especially solar and wind in
It's
2024.
it's the fastest growing technology, but it's still a small percentage worldwide, and only wealthy nations are really investing in it. I don't think you're seeing like tons of solar panels in South America and things like this. So I like to just take you down to Antarctica for a moment here. What you're looking at is two different views. One is in the local summer, which is of course the middle of our winter up here in the north, and then in their cold season. And you can see that there's a significant amount of ice growth around the continent. In fact, the maximum extent of the ice is 18.19 million square kilometers, and the minimum is 1.79 million square kilometers, for a difference of 16.4 million square kilometers of ice that grows every season down there. And keep in mind that what's happening there is the air is getting cold, the water is freezing, and as it freezes, it develops that insulating layer, and that could be anywhere from 1 to 3 meters thick. So if you remember your high school chemistry, um, if we look at water, say, think of this as a freshwater lake, and as the water is getting colder, it starts to freeze at 0 degrees Celsius, and then it stays at 0 degrees Celsius as it's freezing until all of the liquid water has turned to ice. Or sorry, in this case, I'm doing the opposite. I'm sorry. It should be coming from ice. Then it's melting, and it stays at 0 degrees temperature as it melts. And then you add more heat to it, and then you get up to the boiling point. And again, the same thing happens. The water boils at 100 degrees Celsius, and it will stay at that temperature at atmospheric pressure until all of the liquid water turns to steam. And then from steam, the pressure and temperature can rise again. Now, if you do the opposite of that, of course, you have condensing steam, which condenses at 100 degrees Celsius, then cools. And then you have liquid water, and it cools to ice. And in that process here, you see the melting ice has a latent heat of fusion of 334 kilojoules per kilogram. That's a significant amount of energy. And I'm going to talk about that a little bit more in a moment. So let's just look at, again, thinking about the Southern Ocean. If we think of a section of ice being 1.1 meter thick, because as water freezes, it expands. So if we just said that the average of that ice growth was 1.1 meter, and we assume that a cubic meter of ice is pure water with a mass of 1,000 kilograms, then there are 3,600 joules in 1 watt hour. So water releases 334,000 joules per kilogram when it freezes. Now, I don't know if you've ever looked at your winter heating bill, but it's measured in kilojoules. And I did some basic calculations. If you had we've got a fairly large house. If you had a pool of water that had 30 cubic meters in it, and so that's a size of 6 meters by 2 meters by, what is it, 36 times 5. Yeah, anyways, let's say 3 meters by 5 meters by 2 meters, that's 30 cubic meters. Just the energy of turning that liquid water into ice would be enough to heat our home for the whole winter. And then, of course, you've got that ice that you could use for cooling in the summertime. But anyway, converting that to watt hours, it works out to a pretty astronomical number, and multiplying the difference between the spring and the fall in Antarctica, it works out to 1,520,000 terawatt hours. So if you compare that,
what is the total energy consumption of
for
humanity, or the
right,
power?
that's what I'm just going to say here. So compared to all of the energy that humanity used in 2022, 1,520,000 terawatt hours divided by 178,889 terawatt hours is about 8.5 times the amount of energy that all of humanity used. That's being done naturally, and it's not in any way being optimized or tapped by humanity at this point. And a similar amount of energy will be produced in the Arctic in the next 6 months.
So that's
So
roughly 15 to 20 times more than the entire energy usage of humanity.
exactly. So I said, imagine if we could harness that energy and use it to replace fossil fuels. And um, then I say we can, and this is the process. So essentially, you take a working fluid. In this example, I use propane as our working fluid. If we start at point one here and we take liquid propane at atmospheric pressure, and it would be close to atmospheric temperature out here, then we pump that propane under the ice into a heat transfer heat exchanger. We pre-warm it. So as if the temperature is initially minus 40 degrees Celsius, obviously it's going to take some energy to warm that up to the ocean temperature. So we preheat it, and then as it gets closer to the ocean temperature, we can draw up water from the deep Arctic, and even in the Arctic Ocean, when you go down, 1,000 meters or so, you're able to find water that's 3 degrees above zero. So let's say we can bring that water up and
You need to
heat
go
the
1,000 meters
propane.
or just even a little bit under the ice?
Well, under the ice, so the salt water freezes at a slightly lower temperature than fresh water. So the freezing point of salt water is about minus 1.8 degrees Celsius. And yeah, we can definitely just use the local water under the ice, and that would save a lot of money in terms of having to build a large heat transfer tube and stuff. But there's other reasons to do that. But as a proof of concept, you could just use the water under the ice, and you'd lose about 5 degrees Celsius of heat exchange. Anyways, when we do that, I have here a secondary heater and boiler. I won't get into that right now. We can talk about that later. But if we just use the propane at about, let's just say at a freezing point, that's got a pressure, a vapor pressure of about, well, I'll take you to the next slide and talk about it, but vapor pressure of about 4.5 atmospheres. And the condensing pressure, let's say this is minus 42 degrees Celsius, the condensing pressure would be 1 atmosphere. And then what you end up with is a pressure of the difference. So 4.5 minus 1 gives you 3.5 atmospheres of pressure. You can run that either through a piston engine or a turbine. You can generate electricity. And once you got electricity, you can pretty much, there's a lot of stuff you can do with it, including, as we were talking about earlier, run data centers, produce hydrogen, produce light, and so forth. So
And
the next,
yeah, I'm stopping you just because I know that I talked with another friend of mine who is a mechanical engineer who work in the oil and gas industry.
Mhm.
And most power plants that we currently have a much bigger temperature difference. It could be 150 to 300, sometimes even more.
Absolutely, absolutely, and
So
higher
that can
pressures.
generate a lot of energy.
Yeah, so
That
I'm gonna address that right now then. So I would like you to think about wind turbines. Wind turbines operate on a differential pressure of about how much, Ron? How much would you say?
I would say a very, very small percentage of an atmosphere.
Exactly.
Probably less than 1 bar.
Oh, much less. I think you're looking at zero point zero 0.05 of a bar or something like that. Essentially, what they're doing is they're taking the velocity of the wind and converting that into the rotation of the propeller. And by doing that, they actually slow down the velocity on the other side. But if you had a pressure gauge on both sides, the pressure difference would be very minuscule because, of course, it's all atmospheric pressure, right? So they're taking advantage of the velocity to operate that. What I'm getting at by saying that is, wind power has proven to be cost effective. It's one of the least expensive forms of energy. But like the biggest wind turbines we have today are about 10 megawatts of power. So to generate a, um, a gigawatt, you would require 100 of those really large wind turbines. We can use this process and produce a gigawatt in about the same footprint as one of those wind turbines. And the reason we can do it in the same footprint is because you would have heat exchangers going into the atmosphere and heat exchangers going into the ocean. But the base of the structure itself would be, like an oil drilling platform or something like that. So if you consider now 100 wind turbines at 10 megawatts, so you get your 1 gigawatt of power, you think of all the material that goes into that and the labor and so forth, it would be much easier to operate a single structure, even if it's, got these huge heat exchangers and such. Because all of this stuff, the only thing that's moving around is the engine itself, the fluid, but the heat exchangers themselves aren't going to be doing any moving. So this system has very few moving parts, and essentially it's the same concept as a coal-fired plant burning, turning water to steam, only you're doing it at a lower temperature, and you've changed your working fluid from water to propane. Propane in this example, and it could be another working fluid. So let me just go to the next slide
Other
here.
solvent. Yeah.
So this next slide, if you're an engineer, this looks very much like the steam tables, and that's essentially what it is for propane. What we've got is this is the saturated vapor table for propane, and what it is it links the temperature to a specific pressure. And the way to think about this is, if you have a propane bottle, like if you've got a propane fired barbecue, that bottle is in equilibrium, gets to be in equilibrium with the air around it. So if the air temperature is 20 degrees Celsius outside, then because it's contained, the vapor pressure would be about 8.5 atmospheres at 20 degrees Celsius. If you go down to the freezing point of water, so where we're talking about, you're looking at about 4.5 atmospheres of pressure. So this is pressure in megapascals. So 101 kilopascals is 1 atmosphere of pressure, and 100 kilopascals is 0.1 of a megapascal. So I've got sort of a chain of, or a link of descriptions of what's going on at different temperatures. So this is the freezing point of ocean water, and like I said, someplace between 0.42 to 0.45 kilo megapascals, or 0.42 to 4.5, 4.2 or 4.5 atmospheres of pressure. Atmospheres are a nice, easy, even though they're not metric, they're a nice, easy way of thinking about the pressure. So if you look at the temperature in the Arctic, you can pretty consistently get minus 20 degrees Celsius. So even at that temperature, the corresponding pressure of that contained propane would be 2.5 atmospheres. So that gives you 2.3 atmospheres just between those two temperature points. If we go down to minus, sorry, go ahead.
Yeah, so that's not like a coal power plant, but yet a lot more than a wind turbine.
Absolutely, absolutely. And if you take it down to, like I said, minus 42 degrees Celsius, which is fairly common in the high Arctic, you get down to 1 atmosphere of pressure. Now let's go the other way. So I think that we can actually do something I call bootstrapping. So the process that works in your refrigerator is it's a vapor pressure process, and essentially it takes advantage of the phase change of refrigerant to cool the working fluid or cool the space that you want to refrigerate. If you turn that around, you get something called a heat pump, and a lot of people use heat pumps to heat their home, and they have something with a heat pump called a coefficient of performance. So unlike if you burn natural gas, the most energy that you could get, if you just converted it all to heat, you get about 100% heating value from the energy that's available. But when you have a coefficient of performance in a heat pump, you basically can get all the heat of the mechanical motion that you're using to run the pump. So in other words, the pump's going to get warmer, so you can capture that heat, and the electricity going through the wires is going to heat up. But what you're also doing is you're sucking essentially heat out of one space and transferring it to the other. And you do that by boiling vapor at low pressure. Then you compress it. And when you compress a gas or a vapor, it gives off heat. And by doing that, it's a much more efficient process than just burning the fuel or something. You're able to get, if you're only doing a low temperature difference, like 20 or 30 degrees Celsius, you can get coefficients of performance of 8 to 1. So every kilowatt hour of electricity that you put into the system, you're going to get 8 kilowatts of heat, essentially, of heat energy. And that's why a lot of people are looking to move away from natural gas heating to heat pumps. And as I mentioned earlier, if you had, that 30 cubic meters in your garage or under your garage or something, you can use that to heat your house throughout the winter.
If you can convert this energy to
To
a way
heat.
that you can use it. Yeah.
Yeah, so basically, when you convert the liquid water to freezing water, you're able to, by the way, heating something up from freezing temperature to 20 degrees Celsius is even a higher coefficient of performance. So you're probably looking at 9 or 10 or something like that. So it's very efficient if you have something consistently at the freezing point. Now, one of the downsides of heat pumps is when the temperature outside gets really cold. If you got an air-to-air heat pump, the colder it gets outside, the harder it is to operate the heat pump, because essentially what you're trying to do is trying to boil this liquid at a very cold temperature. And even though you have near vacuum that you're drawing off of it, there's just not a lot of energy in the air to make it work. But so that's what I call bootstrapping. Now, what we were talking earlier about was computer equipment. So if we look at computer equipment, you can consistently get a temperature of about 70 degrees. A lot of the computer chips that I have on my computer, for instance, operate happily at 90 degrees Celsius. So if you keep them nice and cool, so they're not producing errors and that sort of stuff, let's keep them at a nice 90 or 70 degree temperature. You get then 26.7 atmospheres. And now, so that's the argument that I have for your fellow who's, an oil and gas industry guy, because 26.7 atmospheres is definitely an easy pressure to extract energy from. And then if we combine this system, if we have on this floating structure a small nuclear reactor, let's say, you can have the entire power plant that would generate. And then when it condenses the water out, you could condense that water at 100 degrees Celsius and then produce propane, which would be close to its critical point, which is 42.2 atmospheres. That is, again, a significant amount of pressure. And if you can then take that, if you go down to, the coldest that it gets in Antarctica, it's in around minus 80 degrees Celsius, we can take that. The vapor pressure there is like 1/10 of an atmosphere. So essentially you're getting, that 42.4 atmospheres, you're able to convert almost completely into energy. And then I talk about harnessing the coldest space. So if you can even radiate energy directly to space and cool at low end temperature, you can essentially get vacuum in your working fluid. So that gives you a really broad range of things that you can do. And by the way, you could have a system that's just running continuously, converting water or converting liquid water into ice, and run that system. Then you can have a separate system that does this bootstrapping, and then have a separate system that's cooling the computers, and have a separate system that's condensing the steam from your nuclear reactor. And all of them can be generating power. So you're only limited by the size of the heat exchangers that you have, and that's in the atmosphere and the ocean, and whatever equipment you're dealing with, like the computer equipment and so forth. All right, so these are the different ways that we can get the energy out of the system. And then once we've got all that electricity, what are we going to do with it? We're in the middle of the Arctic Ocean or the middle of the Antarctic, the Southern Ocean. So, well, one thing that you can do is you can produce hydrogen. Now, if you were someplace where you could link directly to the grid or something like that, obviously you could link to the grid. But if you aren't, and it's not cost effective to build electric lines to where you are, then producing hydrogen is a good way to capture that energy.
Yeah, by the way, just today I saw this green train engine.
Oh, is that right? In Calgary?
Yeah, that's where I work.
Oh, at CP Rail?
It's April, yeah.
Oh, well, fantastic.
CP Kansas City, and I walked today, and I saw the green train. I think they have a couple. Yeah, so one of the idea I can say that since from what I know, if you build a data center in the Arctic, uh, you can have a problem with latency. Like typically you
Right.
want a data center close to the customers, but there are some application that don't care about latency. You need the internet connection, but if the internet connection is slow, but you can do heavy processing there, then
Yeah.
you that's perfectly fine. And one of them is training artificial intelligence, providing that you already have the data.
Yeah.
Another one is crypto mining, Bitcoin
Absolutely.
mining. Because Bitcoin mining can be isolated with a very small link and then use all the power to create Bitcoin or increase the security of Bitcoin.
Exactly. And even though it's a competitive process, it's very rare that, you'd probably be getting down to milliseconds. It's not like you're trading on Wall Street or something like that, where milliseconds are critical. But the price savings that you have by having essentially, if you're able to operate your data center there, the energy from the heat produced can be used, and because you're taking advantage of that huge temperature differential with the cold and stuff, it's quite possible. I'm not saying that I haven't actually crunched the numbers for this, but it's quite possible that you could actually get as much energy out of the system as you're putting into it. And some people might be saying, well, that breaks the second law of thermodynamics. No, it doesn't, because it's just like a heat pump. A coefficient of performance, you're taking advantage of natural process, the vaporization and then condensation of the working fluid. In this case, you're taking advantage of the high temperature that the computer chips are working at and the extremely cold temperature of the atmosphere outside, and using that to run your vapor power cycle. So again, I haven't crunched numbers, but even if you can only get, say, 50% of the energy that you're putting into the computers back, that's better than the current situation where you're
And
getting
even
nothing.
if you don't get any of it, but you don't need to spend energy on cooling.
Exactly. Yeah. So there's that benefit there. So looking at this slide, we've got the hydrogen economy, and I know a lot of people are anti-hydrogen, but I'm one of the administrators with the Canadian Hydrogen Working Group on LinkedIn. And so I get to see all of these great articles, and it's amazing how much is going on around the world in terms of wanting to move away from fossil fuels and move to hydrogen, even though hydrogen is a horrible gas for containing it. It makes pipes brittle. It takes high pressure that you need to compress it to, or if you want to get it down to liquid form, you need to get close to absolute zero, and then need cryogenic equipment. So I'm thinking, hydrogen it has its uses. For instance, obviously you got the Canadian Pacific hydrogen train there, but you can also replace coal in the processing of steel. So in other words, what we're doing right now when we make steel is we use purified coal, and it's called coke, and we mix that in with the steel, or the steel ore, the iron ore, which is just iron and oxygen bound to it. And then the coke essentially burns off the oxygen. So you get carbon dioxide as a byproduct, and then it reduces the iron to pure iron. And then a little bit of that coke stays inside of the iron, and that's what gives us either cast iron or different varying types of steels that have different amounts of carbon mixed into them. It's actually the carbon atoms inside of the iron matrix that gives steel its strength and ductility.
Yeah, I am of the belief that economically hydrogen will not be the best solution for transportation of small vehicle like cars or maybe even truck.
Yeah,
Not sure about train. Train, I think if you can electrify the grid, and probably hydrogen is not the best solution. But if the rail is not electrified, then it could be a solution. Or big container
yeah,
ship, or submarines. It could be something ideal solution.
yeah. And so to that point, they are making, there's a company called Nikola, probably also named for Nikola Tesla, that uses hydrogen, and they're in their trucking vehicles. So basically, tractor trailer type situations. Um, I I know that there are lots of companies that are making hydrogen powered cars. I think Hyundai's got one, and there's several in Europe.
Yes.
Um, but I agree with you. I think hydrogen is not the best option. And if you got your site out in the middle of the Arctic, it's fairly easy then to grab some, nitrogen out of the atmosphere and using cryogenic cooling, which is easier to do in the Arctic as well. Turning that into liquid air and separating the oxygen from the nitrogen. And then you can also collect the argon as a byproduct. And if you have enough of it, you might even condense out some carbon dioxide in the process and capture that for a carbon capture process. But anyway, once you got the nitrogen and you've got your hydrogen from electrolysis, you can use the Haber-Bosch process to form ammonia. And ammonia is a much easier chemical to deal with in terms of the temperatures and the pressures that you're working with. Now, it does take a significant amount of energy to produce the ammonia, but it's also a more versatile chemical. So if you look at the bottom there, you got a concept of a cruise ship powered by ammonia. Well, with little modification, you can use ammonia directly in diesel engines. And a lot of people don't know this, but the official world record for the fastest powered aircraft in the Earth's atmosphere is for the X-15 experimental plane that NASA and US military worked on.
The 1960s, yeah.
Yeah, in the 1960s. So I think, I don't remember the speed that it got up to, something like 2,600 miles per hour or something like this.
I think
Anyway, you can look it up on Wikipedia.
actually it was some phase before the space shuttle. It could even reach space. I mean,
Yeah, that's right.
Not orbit. It didn't get anywhere near orbital velocity, but Mach 8 or something.
There was, I forget the name of the movie now, but it was about Neil Armstrong going to the moon and stuff. It was a few years ago. And it starts out with Neil Armstrong actually flying one of those experimental X-15s. He didn't set the record for the speed of the plane, but that was they made three of them, three models of that. I think one crashed and the other two are in museums or something. But anyways, that was the plane that set the record. And it was powered by an ammonia and oxygen rocket.
And can you have something like jet engine that are powered by ammonia?
I believe you can. One of the downsides of burning ammonia is you could end up with intermediates like nitrous oxide, which you get from burning diesel and gasoline engines as well. And that's why we have catalytic converters on the end. So as long as you have a catalytic converter converting any nitrous oxides after the ammonia burning process, then it shouldn't be a problem to do that. Because nitrous oxide is a much more potent greenhouse gas than carbon dioxide is. The other advantage of working with ammonia is used as a fertilizer. Now, a lot of people don't realize this, but half of the protein in your body was produced artificially. And what I mean by that is it came through the Haber-Bosch process to make fertilizers. And those fertilizers, of course, were taken up by plants, and it helps the plants to make proteins. If we had to rely just on the natural processes for making proteins, the only things that would do it would be nitrogen-fixing bacteria that grow in things like clover and legumes, and natural lightning reacting in the atmosphere to produce nitrous oxides, which then get absorbed by plants. But the point is, every molecule of protein, by definition, has to have some nitrogen in it. And half of the nitrogen in our bodies, like I said, comes from artificial fertilizers. And those artificial fertilizers today are mostly made by using natural gas to strip the hydrogen off of the carbon atoms, and then for the energy to run the process. So there's a significant amount of carbon dioxide produced just to make ammonia. We can make green ammonia without having to do that if we use electricity in a process like I'm talking about here. And so not only can we make fertilizers, then we can also make explosives. And of course, explosives are beyond military applications, are very useful for mining applications. So a lot of...
I see a picture for airship.
Yeah, and so I got the airship there, and we had a whole session previously on this channel where I talked about taking hydrogen and shipping it by air to remote locations, and then potentially using that. You would have then a power plant, say, located up on a mountainside. You would then take atmospheric oxygen to react it in a fuel cell, produce your electricity. So that's your commercial byproduct. But for every kilogram of hydrogen that you react, you're adding 9 kilograms of oxygen. So you're basically getting a huge, like a huge increase in weight for, and then you can, as you convert it to water, and then you can use that water to produce hydroelectricity if you've done that up on the side of a mountain. Or you can also use that water for,
Irrigation.
commercial, irrigation, or drinking water, whatever. So anyway, I was just getting a call. Sorry for the interruption. The other nice thing about that is if you do that in a desert location, of course, there's not a lot of water there naturally. So it's a huge benefit. And the equivalent output of a few gigawatts of power plants. So if we had, say, I don't know, six of these 1 gigawatt power plants and converted everything to hydrogen and shipped it all down to someplace in Arizona, you could support a million people with the output of the water that you produce. I believe those were the numbers that I came up with in the book.
Wow, million. It's good. You can
that's not using the water for industrial processes. That's using the water at the equivalent rate that people in Tucson or Arizona are using, which I think is 40 gallons a day or something like that.
You can water your lawns.
You can more than water your lawn. And then, if you're really judicious, after you've used it to support the people and you got your gray water, well, you can clean that and you can use that for irrigation or inside of greenhouses and this sort of thing. So you can get multiple uses of the water as it goes along. Okay, and then going on to the next slide, talking about water. I mentioned that you're producing this energy basically by cooling down the ocean. And when you cool down that seawater, it freezes. And you think, well, what good is frozen salt water? Well, the beauty is when you freeze ocean water, what happens is the water freezes and the molecules are really tightly packed together when they're in the solid state, and they don't allow the sodium and the chlorine and the other chemicals to get in there. If it's a slow enough process, you won't get any salt inclusions at all. And this is one method of purifying salt water. So you can desalinate it and you get liquid water ice, and then you get cold, salty brine. Earlier this week, I watched a presentation by, I forget the fellow's name, Stefan something, from, I think it was the Potsdamer Institute. Anyways, he's been studying the Atlantic meridional overturning circulation, which is known as the Great Ocean Conveyor Belt that transfers heat from the tropics to the polar regions. And what that does essentially is, you think of the Gulf Stream and other currents going to Europe. Well, if you look at Tromsø, Norway, and you look at Iqaluit in Canada, Iqaluit's on Frobisher Bay and it freezes every year, but Tromsø doesn't freeze. And the reason it doesn't freeze is because it's getting all of this huge amount of energy from this global conveyor belt that is going to the North Atlantic. The warm water evaporates into steam, and as it does so, it heats the air and around it, and then that steam condenses into rain and snow. But what the other process is, because of you're taking away fresh water, essentially, you're producing cold water brine, and that cold water brine falling in the northern Atlantic and the Arctic Oceans is what drives that whole cycle. And a similar thing happens around Antarctica. Anyways, what's happening right now is that Atlantic meridional overturning circulation is slowing down. And we're not even sure if we've actually surpassed the tipping point where it's going to stop entirely. The concern is that as global warming continues, we're going to get more meltwater from Greenland, and it's going to create a cold area in the North Atlantic. And instead of that condensing water going into Europe and warming it up, what's going to happen is it's going to evaporate in the middle of the Atlantic and then condense over the cold water in the Atlantic Ocean and create more fresh water, which will prevent this cooling, this dropping brine that I was talking about earlier from happening. And essentially that will shut down the entire cycle. And
Gosh,
he estimates based
so
on
ba
computer.
yeah, so
Sorry.
basically you're talking right now after energy and water solution about climate engineering.
Right. I'm going to get back to this diagram in just a moment, but I wanted to mention it. So their computer models show that if that circulation stops, there will be places in Europe where the average temperature will drop by 40 degrees Celsius.
Probably
That's
Norway,
crazy.
Britain.
Yeah, basically Scotland to Norway, that area there, most of it's over water. And of course, global warming will still be happening in the south. So Southern Europe will still be hotter than usual, but the Northern Europe areas will become very cold, kind of like Arctic Canada. So that's another benefit of these things, these power plants, is it's naturally producing more cold water brine to help keep that circulation going. So if we build thousands of these, it could help prevent the AMOC from shutting down. So this image here, like I said, when you freeze fresh water, it expands. So a 1 meter by 1 meter by 1.1 meter cube gives you 1 ton of water. And then if we expand that, so a tractor trailer load for most highways in North America, you can put 16 tons of load on your trailer, and that would be essentially 16 cubic meters plus a bit. And then if you take that and you say, well, what if we have 1,000 tanker loads of ice? Well, now we can create these shipments in right on the Arctic polar ice. We build these, and of course, it would crash through the ice eventually because it's too heavy. But essentially, we can make shipments that we can move together and combine them. And what I call a berg here would be like 25,000 truckloads. And then we'd combine these bergs into super bergs. And I can just imagine, so this would be 5 million cubic meters plus 5 million cubic meters of water when it thaws out. So approximately 4,960,000 tons of ice. And I picture this thing, being driven by the power of the wind on the oceans. And we can send it down to, say, the Mediterranean, where, of course, pretty much every country in Europe and Africa and in the Middle East can use extra water on the Mediterranean side of things. So we can take these little shipments and because they're divided into useful literally ship-sized containers, we can send some to Morocco, to Algeria, to Spain, to France, to Italy, and all the way through the Mediterranean to Egypt and Israel. And I know Israel has got it's probably got the best desalination program in the world, but even so, they'd probably be happy to pick up water for a few dollars a ton to
I think
help.
desalination, I'm not sure. I think price used to be something like $1 per ton,
I've seen different rates,
maybe
anywhere from
$3. I don't know.
$1 to $4 is what I've seen, but depends on the process that you're using. But regardless, if you sell that shipment for $1 a ton, that's $5 million approximately, and I'm pretty sure that you can get more than that. And I talk in the book about bottled water. In fact, I think I mentioned it here. Yeah, in 2023, global bottled water sales were approximately $342 billion US. So if you upgrade your water and sell it as bottled water using this process, you can then say, hey, this is green water that isn't depleting any local aquifers. It's not taking any water out of the mouths of natural animals and stuff, and it's not taking water away from the general population. So that's a major selling point, I think, for people looking at bottled water. And you could even take it a step further and say, for this person in Rome who's buying a half liter of of bottled water and we're selling it, say, for 12 and a half cents, which means that the retailer is selling it for 25 cents. Um, we can supply an equivalent amount of water to someone in Africa for free if you buy it for 12 and a half cents profit to us, so 25 cents a half liter. I think that could be a business model that would work. And you've probably seen people talking about, boycott Nestle or boycott this company or that company because they're drawing water from local aquifers or whatever the situation might be. This water is coming to you as a byproduct of producing green energy, and it's not taking any water away from any of those processes I talked about earlier. So even countries like New Zealand, for instance, they have water bottling plants that are located in the rainforest. And you think, well, they have enough water, it's a rainforest. But what they found is it's actually drying out certain sections of the rainforest and hurting the local biosphere, I guess you could say.
Biodiversity or
Yeah,
biosphere.
the biotics of the local region. The other thing that they've got there is they've got agricultural runoff that's actually poisoned a lot of their streams, so it's not really fit for drinking. And this happens in South Carolina too, where they got so many chicken farms and pig farms and stuff that it's polluted the water that's unusable for other purposes. And so any of these places would be happy to buy relatively inexpensive water. So if you look at your like City of Calgary water bill, I think they charge you about $4 per cubic meter. So if we can supply it for even $2 or $3, there's money to be made there. But beyond that, there's a humanitarian cause that we can do. There's lots of groups like I mentioned. There's 2.2 billion people in the world today don't have access to reliable, clean, safe drinking water.
If you can go back to the airship, if you fill up
Okay.
an airship with hydrogen and
Yeah.
transferring for the plane to Sahara Desert, and
Yeah.
then have some kind of power plant that take hydrogen and oxygen and make water.
Yeah.
Is this any significant? So you produce local energy and
Well,
you
so,
make water from the hydrogen and that is
right.
reacting with oxygen. How
I would
how
say
much
that
water?
using airships would be a good idea for any way that's more than say 100 kilometers from the coast, let's say. And the reason I say that is because if you're in Algeria or any of those Saharan countries, you have lots and lots of solar energy. And you are also bordering the Mediterranean Sea. So just like Israel is doing, you can produce cheap water from desalination using solar energy. So there's no need to bring the hydrogen there. You can produce your own hydrogen or you can produce your own water in those processes. But if you're starting to go inland, if you look in the, say, the Kalahari Desert or, the southern part of the Sahara Desert, the Sahel, certainly it becomes a more attractive prospect in those situations. Or even if you look at something like, Saudi Arabia, they're talking about NEOM, which I don't know if it's a viable project. Everything that I see about it it makes it unlikely for me to imagine it happening. But let's say it gets built, well, it might be more cost effective to fly your hydrogen in to the far end of that line than to ship it across from the Red Sea or whatever. So it's just kind of an out of the box thought. The other thing that I thought about, of course, in the Arctic, in the wintertime, you've got ice everywhere. So if you want to get anything out of there, if you want to do it by ship, you have to have an icebreaker. The other thought that I had is we could make submarines. Submarines are essentially pressure vessels. Fill them with hydrogen and other goods, because if you fill it with hydrogen, it'll just want to float. But you fill it with hydrogen and maybe fish or some other product, ammonia, let's say, then at least you can get it below the ice, and the ice isn't terribly thick, so you don't have to go too far. But then you can get that out from wherever you're producing it to whatever market you want to go to. And once you're free of the ice free zone, or once you're free of the ice zone, you can just surface and operate like a regular ship. Only, again, all of these things that I'm talking about, whether it's the water or the dirigibles or this submarine, they could all be autonomously powered craft. And so you don't need to have a big crew, and that's just another expense that you can save. This could all be, power being shipped independently and not have a huge amount of expense. Of course, when you get to, say, the Port of New York or something like that, you'd have to have a pilot come on board and take control of it, but that's not a big deal if you can save the shipping costs for the rest of the way. We have the technology to do that. Lots of similar things are being done. I mean, just look at the drone attacks that Ukraine's doing, using satellite navigation or something.
Yeah.
All right, so I think we've talked about this already. So the next thing is, if you got all of that electricity up on the polar ice cap, besides making hydrogen and ammonia or other chemicals, well, you can produce light, of course. That's easy enough. Everybody's probably watching this using electric light. And because you got the ocean right below you, you can suck as much heat out of the ocean using a heat pump as you want to. So the only thing that's limiting you from growing stuff is, the heat exchange to the outer atmosphere. So you build a well-insulated shipping container. And then you need to have some water. Well, we just talked about that. And we need to have some fertilizer. Well, we can produce ammonia there, but we can bring in other fertilizers like phosphorus or whatever chemicals. And if we don't bring them in, they're almost all available in ocean water anyway. So we could probably extract them from there. Essentially, what we've got then is a completely controlled environment that we can grow food in. And this has been done in a lot of instances. You can use high efficiency LEDs that produce light that the plants love, and essentially turn the Arctic Ocean into a breadbasket for feeding the world. Now that's on top of the ice. What can you do below the ice? Well, this is a mid-Atlantic or mid-ocean. I'm not sure where this platform is actually located. Mid-ocean fish farm. So one of the advantages of growing fish in the deep ocean is that, one of the disadvantages of growing them in shallow areas is that when you have thousands of fish and they're essentially pooping in one area, that those toxins build up and make the fish sick and deplete oxygen from the local waters. So if you do this in the deep ocean, as those things fall down to the ocean floor, they get dispersed and it doesn't cause the same kind of toxicity. And plus, of course, you got ocean currents that are going by, replenishing the oxygenated water for the fish. So you'll have fewer diseases and healthier fish. So this is an example of open ocean, but you can do exactly the same thing with an ice cover. You can hang the nets from the ice or have them suspended below the ice and grow your fish. And I also talk about, people don't think of this either, but it turns out that the Arctic Ocean is a great place to grow algae and kelp. In the springtime, when the sun comes up over the polar ice cap, the sun shining through the ice is enough to trigger life processes in the algae, and you get mats of algae growing underneath the ice. And those mats of algae then get eaten by copepods and other different types of plankton and all this stuff. And that's the basis of the food chain. By the way, the reason that we like to eat fish, or one of the reasons that we like to eat fish, and it's a healthy thing, is because it's full of omega 6 fatty acids, right? Omega 3s and omega 6. Yeah. And those fatty acids aren't produced in the fish. They're actually produced in the algae. So if you wanted to just produce those oils, you could literally grow the algae and process the algae, and then you don't get the bioaccumulation of mercury and other toxins that you get from eating
fish farming in shallow water.
Right. But in the Arctic Ocean, those toxins, the mercury and those other things that are prevalent in, you probably don't want to eat fish from the Pearl River Delta in China, or you don't want to eat fish that are caught in the Baltic Sea in Europe, because that's basically a closed sea that doesn't have a lot of all the toxins from all the industrial processes of the neighboring countries end up in the Baltic, and they don't get flushed out into the Arctic, so, or the Atlantic, very much. So they basically build up, and essentially, I think there's warnings that people shouldn't eat fish that are caught in the Baltic Sea. But interestingly enough, they catch fish from the Baltic Sea, and then they grind them into fish meal, and then they feed them to, fish farms in Norway and other places. And they say, well, this is a natural process, but those toxins are still in the food, and so those salmon build up those toxins as well. In the Arctic, you can have that entire food process, and the salmon aren't eating other fish; they're eating copepods and such things, and so they're not building up those mercury and other toxic chemicals to the same extent. Right, and so going back to the previous slide for a moment, so one of the beauties of, first of all, land up in the Arctic is essentially free. If you want to go and homestead, there's still opportunities for people to go homesteading in Canada. Of course, the Arctic Ocean, there's places that are international waters, and you could, be a seasteader out there. And same thing if you go around Norway to the, what's the name of the islands up north? Anyways,
Yeah.
there's a group of islands up north that there's the Svalbard Treaty.
Everyone can go there.
Exactly. It's basically an international zone that's administered. The administration is by Norway, but the international treaty says as long as you got a passport and you can support yourself, anybody could go there to live, and not only live, but you can mine or do other activities, economic activities up there. So you don't become a Norwegian citizen if you live there or anything like that, but anybody from around the world can go there as long as they're not criminals and so forth.
Yes, I know
And
the Soviet built those spy stations.
yeah, so the Soviets have been operating a coal mine at a loss for years in in the communist days, and it's still today. Russia operates the. I'm saying still today. I don't know if it's still going on since the war in Ukraine, but they used to operate a tour guide or guided tour through the old mining complex, and you can look. You go to the school and it's got books from the 1950s or something, just all over the place, and it's kind of like going through an industrial ghost town of the Soviet Union. But the point is that there are places you can go in the Arctic. You don't have to pay, property tax or, and even in Canada, you have reduced income tax if you live in the Arctic. So, reason I mention this is both Ron and I are fans of science fiction, and Ron has had Robert Zubrin on here before, and of course, Robert Zubrin wrote The Case for Mars many years ago. And he was the head. I don't know if he's still the head.
The Mars Society. Yeah.
Yeah, he started the Mars Society, and the Mars Society actually operates a place on Devon Island, and they purposely chose Devon Island because it's extremely remote, so they have to be self-sufficient, just like they would be on Mars. The temperature can mimic what life on Mars would be like. So, a typical day on Mars, you're looking at about -40. Well, in the winter, you can get those temperatures up there. And like I said, they're purposely isolated so that if somebody breaks their leg or something, they have to deal with it themselves, because the nearest help is over 350 kilometers away, and they'd have to send a helicopter or something, assuming that the weather is good enough that they could do that. So, anyways, since Elon Musk wants to set up a colony on Mars, the Arctic is an excellent place to prove out a lot of these technologies. And so, these greenhouses that I'm talking about, self-sufficient food production in a remote location, you might not be able to use the ocean for your energy, but you can probably still use solar panels or something out at Mars, even though the light is significant.
Yeah, I think nuclear is probably the best solution for Mars.
Yeah, so nuclear would be perfect, because then you have a compact, dense energy source that lasts for decades, and then you can produce your own food locally, pressurize your buildings, and all the rest of that. So yeah, the drawings are just some mock-up drawings that
Yeah.
I did for a project I was working on.
Now,
But
Titan, the moon, one of the moon of Saturn, that one actually have lakes for methane.
yeah, they got
Or you can
methane lakes.
maybe you can build some similar process instead of nuclear and use temperature differentials to
That's true.
generate energy.
Although I don't know how well it would work at cryogenic temperatures because methane liquefies at, I don't know, -100. I don't know what the number is.
Yeah,
I think
it's
it's
I
well
think
below.
average temperature there is -70, so it's definitely not like the Arctic.
Yeah.
But the same
But
principle could maybe work instead of using nuclear energy for everything. You can use geothermal.
yeah, one of the interesting things about Titan is that its atmosphere is very dense and it's got mostly nitrogen in the atmosphere. That's why it's got that orange colored haze, um, uh, and well, hydrocarbons and stuff in the atmosphere as well. But yeah, like you said, because it's going around Saturn, it's got pretty strong geothermal energy because of the tidal forces, and you could presumably tap into that. I don't know how it compares to say Europa or Io. I mean, certainly I think it's a lot less tidally locked than Io is, or not tidal locked, but you know. The tidal forces are significantly less than Io. Io is kind of close to the Roche limit where a moon would be torn apart and turn into, rings like around Saturn. But anyway, so
Yeah,
there are different places you can go in the solar system to set up colonies, and the Arctic is an excellent proving ground for that. Because yeah, it doesn't get down to cryogenic temperatures, but it gets pretty darn close. In fact, this is very interesting. In Antarctica, the temperature has naturally gotten so cold that if you walked out and breathed a breath out, the carbon dioxide in your breath would fall to the ground and turn into solid carbon dioxide. It,
dry ice.
yeah, it turns into dry ice. So, that's I have an idea that
Yeah.
I'm missing out because Elon
No.
Musk and the X Prize, they have a competition to do carbon capture. I talk about it in the book, but I think that the Arctic is a perfect place or Antarctica in particular is a perfect place to extract carbon dioxide from the atmosphere because you're so close to the temperatures for much of the year where it just naturally precipitates out of the atmosphere anyways. Of course, when it warms up, then it just turns into carbon dioxide gas again. But if you can capture it in its solid form, that would be a great way to uh, take carbon dioxide out of the atmosphere with very low energy inputs. All right.
Yeah.
Was there anything you want
Yes.
to say about Robert Zubrin and the Mars Society?
Yeah, I think they are now starting some kind of a university or some kind of a project that I heard Robert Zubin talking about developing technology that would help to colonize Mars,
Oh,
but at the same time they can help uh, Earth. And one of the main projects that they are working on that I know is what you are talking about here. Is growing up plant in a very confined, dense greenhouse or something like that.
mhm.
That probably will require some robotics, genetic engineering, irrigations, artificial irrigation, artificial light, and a lot of genetic engineering. So you can put the plant could be a lot smaller and produce more food for the same amount of energy and space and water.
Exactly.
So maybe you want to engage the Mars Society and see if they
That sounds great because I
yeah.
know Elon Musk is a supporter of the Mars Society. I'd love to get in touch with him and talk about these ideas. Uh, and another thing that we can do, and this is maybe counterintuitive, but you think of, I'm a huge fan of SpaceX and what they're doing with Starship, and we've just seen the fourth launch of Starship, and essentially it was, I mean, obviously it wasn't a complete success, but it pretty darn nearly was a complete success, apart from tiles melting off and stuff, but it still essentially completed its mission profile. So one of the detractions that I've heard people say is, well, these rocket scientists, these companies, these billionaires are doing these big showy things, and just look at how much pollution each launch puts into the air in terms of carbon dioxide and this sort of thing. What if we produced green methane? Like I was just talking about, we can capture the carbon dioxide out of the atmosphere. We can hydrolyze the ocean water to get
Methane.
the hydrogen, and then you can turn that into mixing carbon dioxide and hydrogen.
Yeah, that's pretty much what Elon was talking about, and also Robert Zubrin. It's called a Sabitar reactor. That you take energy and you take carbon dioxide and water and turn it into a methane. This is
Yeah,
also how they plan to produce rocket fuel on Mars.
yeah,
So I
and so
think the
there,
idea is to make the rocket launch from methane that is produced locally
yeah,
with solar panels or other
yeah.
green energy.
Well,
So the
even
each
nuclear
launch will be,
reactors. Yeah,
yeah, so each rocket launch will be carbon neutral. So
that's right.
it will produce carbon dioxide, but it's carbon dioxide that was taken from the atmosphere. So
So he's already thinking along those lines. So yeah, if you have this abundant energy source in the Arctic, by the way, again, to liquefy methane, if you do it in a cold environment, it's a lot more energy efficient than if you're trying to liquefy it in a warm environment. So doing it in the Arctic again makes sense. And yeah, so I think the chemical process is carbon dioxide with hydrogen turns into methanol, and then you can replace the OH with another two hydrogens, and you get methane and water. And so the chemistry is actually relatively simple, as I understand it, and all of that can be done up in the high Arctic. And then that argument about polluting the atmosphere when you're launching rockets goes away. Oh, and by the way, all of a sudden, if you're able to launch rockets and use them for transporting people around the world in half an hour, that's and you're able to do that with green methane, well, then you're already more efficient than the airliners are, because we haven't really figured out a way to get jets to
ammonia.
go intercontinental. Yeah, I guess you could do ammonia, but again, I'd be concerned with ammonia because now you're releasing those nitrous oxides in the high atmosphere. You're not going to have a catalytic converter on a jet, right? Like if you watch that X-15 flight, you can see the exhaust coming out of the back of that was orange.
Yeah,
It was
the other option is uh, hydrogen.
Yeah. So you can do hydrogen, but again, hydrogen has its problems because of the pressurization and all these sorts of things. Hydrogen airships are great if you're willing to go a bit slower. But hydrogen aircraft, they're working on them. Don't get me wrong. Like I said, I'm following what's going on in the hydrogen industry, and there are several companies that are developing hydrogen powered aircraft. But for the most part, as I understand it, they're kind of like, for flights within Europe as opposed to flights between Europe and Asia or Europe and North America. So relatively short hop kind of flights.
Yeah, so you say methane is the solution for long
Well,
distance
methane
flight.
is the solution for rockets. And I think Elon Musk chose methane specifically because he wanted to be able to produce methane on Mars to have a return flight. That was one of the considerations, at least.
Yep.
Yeah, so very interesting. And then so we'll skip the fish farming here and just go on to the next slide. So the stuff that I've been talking about in my book, I make a case that we can promote every one of the United Nations Sustainable Development Goals. So zero hunger, we can produce extra food. Good health and well-being, we can produce healthy food, healthier food. Clean water and sanitation, we talked about that. Affordable and clean energy. So this is probably the biggest one, because once you solve the energy problem for the people, they can do anything. I mean,
That's directly related to poverty, to eliminating
exactly.
poverty.
Yeah.
Because
So
every society that become rich use more energy. So I don't know what is the cause and effect, but probably they are interrelated. So if you
right,
want to have a rich society, you need cheap, abundant energy.
right. And so when you got that cheap energy, that promotes decent work and economic growth, promotes industry and innovation. And by the way, this whole process of building these green power plants in the Arctic would be a huge construction project and infrastructure project. Reduced inequalities. Well, again, if you're making the poorer people wealthier, that reduces inequalities. Sustainable cities and communities. We have enough energy through these processes that we can completely get off of fossil fuels, and that would make us sustainable. Responsible consumption and production. Well, I can't think of, we in this, through these processes, we can have abundant water. So that becomes a major life enhancing quality. And then when you've got abundant steel that's not polluting, when you've got abundant computer power and artificial intelligence, of course, those things are going to improve our lives and make our lives more efficient, and make it more efficient to consume stuff. Climate action. We talked about you're removing carbon from the atmosphere. We talked about reducing fossil fuel consumption. We talked about strengthening the ocean currents.
I
Life below
remember
water.
from the book, I remember you talking about their strategy to reduce the intensity of hurricane or other tropical storm
Yeah,
that could be devastating.
I didn't want to get into that because we could spend 40 minutes just talking about that alone. Um, but yeah, there's got to be a reason for people to still go out and buy the book, Ron.
Buy the book.
Life below water. So if we are able to produce farm-grown fish that are healthier than most of the farm-grown fish today, and at least as healthy as the wild-caught fish, and we can do it more cost-effectively than even going out and catching wild fish, that reduces the pressure on natural populations, and that improves life below water. Life on land. If we can grow abundant food in greenhouses, that means we don't have to continue cutting down forests to grow farms and to grow food on farms and stuff like that. And so we can feed the world and turn the Arctic Ocean and the ocean around Antarctica into bread baskets. So all of these things lead to better justice. Of course, all of these things are international cooperation opportunities. They help to eliminate poverty and eliminate hunger. So I think, and then so when you got all those things, of course, things like education. Well, now people will have access to computers and more energy. Gender equality. Well, I think as countries become more affluent, it's a natural process that women tend to get better rights. Now, there are some cultures that maybe that isn't the case, but I would argue that there's a case to be made that improving abundance and education and stuff will help gender equality. So all of these things are promoted through these technologies that I'm talking about in the book. So yeah, what does that leave us with? One more slide here. This is Peter Diamandis is one of my heroes, I guess you could say. I haven't met him personally, but I intend to change that. So these are some of the quotes, but I'll start with the one from Dr. Sultan Al-Jaber here. Rewiring the energy system is a multi-billion-dollar business opportunity. Sorry, multi-trillion-dollar business opportunity that is good for the climate, good for humanity, and good for sustainable economic growth. And I'll just add to that, the Alberta government estimates that by 2050, I think it was, the hydrogen industry will be worth $11 trillion on its own. That's significant. And that's coming from a province that is heavily into oil and gas. And Alberta wants to be a leader in hydrogen development. So yeah, there's some opportunities here. Right now, they're mostly focused on converting methane into hydrogen and graphene and stuff like this. But obviously, if we can do this without even having to involve fossil fuels, all the better. So Peter Diamandis' quotes, the world's biggest problems are the world's biggest opportunities. I say I'm dealing with some pretty big problems here. The best way to become a billionaire is to help a billion people. Well, if we can supply 2.2 billion people with drinkable water in quantities that they need, that is definitely helping them. And then he says, imagine a world of 9 billion people with clean water, nutritious food, affordable housing, personalized education, top-tier medical care, and non-polluting ubiquitous energy. Building this better world is humanity's grandest challenge. Well, that's the challenge that I'm trying to develop here and solve. So I like to, just here at the end, I'm looking for the right partners to make the world a more sustainable and livable for the humanity. And let's do this and get rich together. But
How, question, how much do you
yeah,
think a chat platform would cost to construct?
in the book, I say the prototype platform, and I just pulled numbers out of the air because I didn't have the time to go into a deep
This is
dive.
for business investor who are looking at the
Right.
channel.
So I say, okay, let's say that the first one, if we look at, there's an oil platform that the Russians are operating. It was built by Americans, and it costs $12 billion, and it's designed to operate in the ice zone. It's called the Berkut oil platform, and it's in the Sea of Okhotsk. And it costs
So
$12 billion. So I figured the same for the same investment, or sorry, I figured let's take that as a starting point and say, okay, let's make it built for more extreme environment. So we'll add 50% to that cost. That brings us up to $18 billion. And to make it a nice round number, we'll put $2 billion as a contingency fund. So for the sake of argument, $20 billion to build the first one. And I want to stress that I think that's an outrageously high estimate. So let's assume that we can do that and it produces a gigawatt of power. Well, that would make it one of the most expensive forms of energy that we have available to us. I don't have the chart here, but I compare nuclear power to wind power and solar power and coal-fired plants and stuff. There's a chart that you can see on Wikipedia that I essentially copied in the book. And I said, okay, that's the prototype. But from engineering, we know that once you've got a good design and you go into mass production, well, that cost will drop significantly, and it can be as much as 10 times. So let's say that we can produce these things for $2 billion a piece. Now that is a 10% of the original cost that I was talking about. And that still has all of the life support, all of the accommodations, the food, the fitness training areas, the communications, all of the stuff that you need for people. Now let's take it a step further. Let's say that we can turn these energy platforms into autonomous structures. So if you imagine, like, wind farms hardly need any human interaction at all, and we can build hundreds of these things, and you get away from all of that life support infrastructure. So essentially, you've just got a platform that's running, generating power and producing all of these things. And you have robots that might be operated through telepresence or something like that, or through artificial intelligence. Now you can drop that cost down to maybe $200 million. You're literally just paying for the equipment to that point. That would make it the cheapest form of energy on the planet.
and what if we can build data centers?
Yeah, so the data centers can be autonomous as well. Like the data center that Microsoft operated under the ocean, I think it was operating for 2 years without any interference, and then they brought it up to clean it and stuff like that and change out some equipment that had broken. But so you can go for extended periods of time without having to do anything physically with your data center. But the data center would be
You need to
operating.
replace disks and drives and stuff like that.
Well, okay, so you send it up there and you've got hot swappable drives or whatever you need, and you have robots that are able to move stuff around. And I don't think that you need a lot of people. But even if you did, let's say you have one platform that's got life support and you got 20 platforms around it that are all autonomous. So the people who are working on that platform with people can go and service the other platforms. So that still reduces the costs significantly.
Yeah, and I have one more question, if that's okay.
Yeah.
Uh, the design that you currently have will work 6 months a year, right? It can only work in the winter.
Yeah. So I've been thinking about that. Yeah. So it works in the winter and then you do a transition. So pretty much all power plants have to shut down once a year for servicing and maintenance and stuff. So this power plant would operate, say, in the Arctic in the winter here, and then you'd have a 2-week transition and go down to Antarctica. And in that 2-week transition, you're able to swap out equipment and repair stuff and replenish the hard drives like you're talking about. And you can still operate your data center because you're going to have nuclear power, say, on site, or you can
Or
just use,
solar
or you,
panel.
Yeah, you can have solar panels, or you can just use some of that
Because in
hydrogen
the Arctic,
produced.
during the summer, you have a lot of sun, 24 hours a day.
Right. So that's the second idea I was going to get to. So this system is designed, it's optimized for cold weather, but you can design it. So the first option is you send it down to Antarctica, service stuff, you send your fish and all the other stuff to market, and off you go. Because you can freeze the fish at minus 40 degrees, flash freeze it, just like the bird's eye process that was developed years ago, which has very high quality frozen food. Um, you flash freeze it, and you can keep it for as long as you want in that state, right? But every 6 months, you're going to be going back and forth in that model, and you do the same thing in Antarctica and so on. The other option is you just build a permanent site, and I do talk about this in terms of like tourism and stuff. So you build a site at the North Pole or close to the North Pole, so you're not like getting in conflict with Russia, let's say.
Or with
Um,
Santa.
yeah, exactly. So we got Santa Claus, and I could see Denmark and Canada building straddling our border, just like we've got that island that I forget what it's called now. It,
I remember
for
it looked like
years,
the Millennium Falcon.
yeah, there was a conflict in terms of Denmark and Greenland and Canada. There's an island that basically goes right down between the two of them, and whoever controlled that island would control the sea around it. And of course, the ocean floor is full of all sorts of mineral wealth. And so they were going back and forth, and what was it called? The Bourbon Wars or something like that, because the Danes would leave Cognac with a flag and say, this is Danish territory. And the Canadians would go up and leave Canadian Club and say, this is Canada's territory. And after Russia attacked Ukraine, they said, this is ridiculous. We're friends and allies. We're both parts of NATO. Let's show the world that we can come up with a solution. And what they did was they said, okay, there's a natural fault line down the middle of this island. Let's just say that's the border, and we can share this and stop this silliness. And that's what they did. So I can imagine like Denmark and Canada collaborating to produce like a tourist area, which would have, if you imagine like a Disney theme park with Santa Claus, of course, that's a perennial thing that would be a tourist draw. But so you have Santa's workshop up there. Literally, it would be a working workshop, and it could bring toys from around the world and assemble them and have stamps and sell them around the world saying this was made in Santa's workshop. Um, but the other thing that you can do up there is, like you said, in the summertime, around the North Pole, you got 24 hours of sunlight. Solar panels. The biggest complaint about solar energy is that it's intermittent. Well, it's not intermittent for half the year up in the Arctic. So you can, in the wintertime, you can produce the energy from the ocean. In the summertime, you can use solar panels or concentrated solar. And you remember all that ice that we created in the winter? Well, that could be used to condense the steam and give you a vacuum essentially on the downside of the steam cycle. So you can condense it on propane. You can still run a propane cycle between 96 degrees and 0. So that's, remember, if we were talking 42 atmospheres of pressure down to 4.5 atmospheres of pressure at 0 degrees Celsius. So that's significant enough to produce a lot of power. So you could run the steam cycle and the propane cycle and basically thaw out all that ice that you
And if
produced.
you have some surplus energy, you can store it as hydrogen and then use a power cell to convert it to
Right.
power and run the data center or whatever is there.
Yeah. And so like you can still have those SMRs, the small modular reactors producing energy. So you don't even need to have all the battery backups because, like you said, the hydrogen is itself a form of battery backup. Um, so yeah, you could do that year round, or you can do the travel between the poles model. The advantage of doing it year round is now you can grow things like lobsters and crabs that have multi-year growth cycles, and they're happy to eat the waste products of when you clean the fish and stuff like that. So you can have an entirely new food cycle based on that.
And
And so,
data center, you cannot move to between ports, it has to be stationary.
well, no, I would say you could, because as long as you can link to Starlink or some other telecommunication system, you can upload the data as you need it, right? Like you said, with Bitcoin or any of the cryptocurrencies, you're just basically putting a small amount of data back after you've done all that number crunching and won the lottery
Yeah,
there.
but you don't want to leave the computer turn off 6 months a year.
No, 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 no. Yeah, I mean,
I
you'd
mean,
still operate the computers, of course.
to be bring it on a ship and then transfer them from one pole to another.
Well, the whole thing would be a floating structure that would go down. The way in my mind, I've got like I left it purposely vague. You know, the idea is I don't want somebody necessarily to go out and develop this without me. I'd like to still become at the very least, be a consultant in the project. You know,
Okay.
so I've got ideas on how that could all be done as well. Um, but yeah, that's pretty much in a nutshell. And I don't know where we have an hour and a half or something of edited footage here. That's it. And if you don't mind, I got a
Yeah,
little,
yeah, that was my next question. Where can people find you? And
yeah.
either
So
to follow what you do or if they want to invest 12 million, 18 billion, 20 billion.
well, I've talked to several people about the best way to do this. And I think the best way would be to do a proof of concept on a smaller scale, maybe 100 kilowatts, and be able to power a small community in the Arctic. And so Northern Alberta, Northwest Territories, Nunavut, and Yukon Territory all have indigenous communities that are living near large bodies of water. That's all that you need. It doesn't have to be salt water. If we want to do this on Great Bear Lake or Great Slave Lake or the Mackenzie River or the Arctic Ocean, doesn't matter. Any of those sites will work quite well. All you need is liquid water that you can freeze to produce this energy. So
Yeah, so I'm going to put a link to the Foresight tag, the link that you gave me earlier.
yeah,
The link to the old video that we did when we spoke about airships, if people like big airship with hydrogen, and the link that you post here to how people can follow you and find you.
yeah.
So I just want to say thank you very much for being here and giving this presentation.
Well, I'd like to say thank you, Ron, for going out and buying the book and having enough interest to do a second presentation here. I
Yeah,
really
and
appreciate
hopefully you can help save the world or
it.
increase
I,
prosperity,
I, I,
hunger.
I always I laugh when people say save the world. I think that's a silly concept. The world will exist long after humanity's gone, but I hopefully that we can live in greater harmony with the world and promote life in human form and in animal form and in plant form without polluting this place that we live in. So,
Okay, so thank you very much, and looking forward to your next book.
yeah, we'll see when that happens. I think I hope that I'm too busy to write another book for a long time because I'll be developing these ideas.
Okay, thank you.
Okay, thanks, Ron. Bye bye.